Hi everyone, so in this video we are going to talk about the Newton Raphson method and how we can use this method in order to find out the roots of equation. And this method is actually derived from Taylor's expansion. If you can see the Taylor expansion here, and we just omit this term and we find out we just omit this term and this O term, and then if we simplify this equation for x I plus 1, here you know that this delta x is interval between the next value and the previous value. So if we solve this equation for x I plus 1, then from here we can get this value. So this is the same concept. Uh, we actually use this function in order to find out the next values. I'm sorry actually if you hear any voice or any call, because I'm right now in my office and this is the early morning time and there are a lot of people here. So I'm sorry for any distraction if you got distracted by any of my cell phone and some of the voices nearby. Anyways, so we can use this expansion and this formula over here in order to find out the next value, where this is the first derivative and this is the function itself, and this is the next value of x. So we actually put some trial value of x and we find xi plus 1, and then we keep on doing this procedure until and unless we have the minimum approximate error or the true error. So let's solve one example, or the same example that we have by using the Newton Raphson method. Okay, so let me open the Excel. Yeah, okay, again I'm sorry, as I mentioned you that this is the busiest time and I'm preparing this tutorial for you, so please excuse me for all these distractions. Okay, so here we have the same example that we discussed in our previous previous tutorial. So we have to, this is the question that the function itself is the same as in the previous example, and this is the first guess of x, and we have to use the Newton Raphson method in order to find out the root of this equation. Okay, so let's go, and we have the same expression here. So let's say this is the trial or iteration, you can also call it iteration, and then this is xi, and we can have true error and then approximate error. Okay, so let's say the first iteration, we have the initial value of x, that is 0, and then the true error we can find this later, but or we can write this expression right now. Let's keep it for the later, and the next iteration we can get this value plus 1. This is next iteration, and how we can find out the next value using Newton Raphson formula. Using this formula, for example, we need the derivative and we need the function itself. So the derivative of this function is actually let's put it here. The derivative of this is the function itself, and then the derivative, I just wrote it for a minute, just Control C, Control V here. Okay, so the f dash x would be minus power x minus 1. Okay, so now I mean in order to apply this formula, you can either isolate all these expression, or like you can first find fx, you can find f dash x, and then By using this you can find xi plus 1, or you can use the previous technique. Like here we can find xi plus 1, but if you are not comfortable and you're worried about doing any mistake in putting the expression, so you can find these values separate, or you can combine them. For example, what I mean, so for example here you can add one column, say fx, and you can add one more column, f dash x, and then you can also add here xi plus 1. So instead of putting here the xi plus 1, we use this one, and then we keep on computing, and here we will get the previous value. Okay. This is a technique. If you are comfortable, you can just put the whole expression here in this cell. I leave this up to you. So it's your choice that whether you want to use the these split form of sheet, or you want just these three, 1 2 and these two columns in order to find out the solution. Okay, so I think this is much easier because you can control your values and you can understand that whether your values are correct or not. For example, if I put f of x I here, and here I put, okay, so 2.718 raised to the power minus xi minus xi. So this is actually fxi. Okay, it makes sense. And now let's go for this. So here it will be, okay, let's check first, because minus 2.718 raised to the power minus xi minus 1. So here it should be minus 2, but it's coming 0 because as per my information here there should be a minus 1. If I put minus 1 here and make that function separate, for example in this way, so it should work. So yeah, now it's working. Okay, so here if you can just put the whole expression, then it will become x. Now here I can apply this formula, xi minus fx over f dash x. So if I apply this whole formula, it will become xi minus fx divided by fxi. Okay, so it becomes 0.5. so this is actually the new root. You can also apply, for example, now the equation for true error, because now you have the true value. The true value was in our previous sheet, we have used it. It is here. For example, the true value of the error is the true value of the root is, we have it here. So let's compute true error. This is equal to ABS true value minus this value divided by true value, converted into the percentage. Okay, and then you can also compute the approximate error. For example, in the approximate error, now you can find the current. This is actually the ABS current value. This is the current value minus this is the previous value divided by the current value. This is the current value. Okay, so we have one convert into the percentage and go for two significant more digits here. Now for the next case, xi, this will be the xi. Okay, so just put this cell equal to this one, and then just control C and control V. So it is now the true error is 0.14% and the approximate error is 11.71%. I do now copy paste for this cell for here, and let's see what happens. So you can see in the third trial the values are very close to the true values. The values have been almost converged. For example, it is 0.614 and the true value was 0.567 something. So up to 3 significant digits we have the same values of the root, which makes a solution close to the accurate one. I'm sorry. So this you can see that the value of the function is also becoming 0, so which shows that the roots are becoming converged and they are now becoming the accurate, and now you can use it for your purpose. So this is how we use this Newton Raphson method in order to find out the roots of the equation. So let me write here. The other way that I was saying, for example, if you are sure about your solution, for example, let's use these two columns here. Okay, and instead of dividing this, I'm solving the same question but with the other way, that if I say this is xi plus 1 and this is xi, so here I should write the expression, and that would be xi minus, so this is f of x, this is 2.718 raised to the power minus xi, this is xi, divided by minus xi divided by, say, minus 1 multiplied by 2.718. Why I multiplied by minus 1? Because there's some restriction over here. Okay, minus xi, I'm not feeling well in my throat, I'm sorry. So minus 1, and that's all. So this is how we can find the roots, and then how you can calculate the true error and the approximate error. Just copy these expressions here, for example. Okay, it's fine. This is, and here the approximate error, we don't have the previous value. We can say for this case we cannot compute the approximate error. For this case we can compute, this is the current value, okay, minus this should be the previous value, okay, 100%. So this is how we can use. Okay, you can see it's converged into the second trial here, or the third trial, and the values are pretty close, like the approximate error and the true error, and the value of the root is the same as we have received. So this is a very short demonstration that how you can split your answer and how you can split your question into the different parts, and you can use it for the solution. So this is the same technique for the Newton Raphson and for the other methods that we will use. Okay, so the next method is the secant method. So in the secant method, it is actually the same method like we have discussed in the Newton Raphson, but the only difference is that we put the definition of derivative. For example, the definition of derivative is this here. You can see actually it is written in the inverse way. There's a mistake here. There should be fxi minus fxi minus, for example, this definition is not correct here. It should be up and this should be down, and if you put it here in the denominator, so you will get this value. So this is actually 1 over f dash xi. I hope you understand my point. Okay, so this is the same Newton Raphson equation here, but if you put the derivative value, like this is the definition of derivative, you will get this equation. Okay, so let's use this secant method in order to find out the roots. We have the same question. So this is the previous value 0, this is the next value, for example xi minus 1, and this is xi, and this is the function itself, but now we have no derivative. We don't have to take any derivative, we don't need any derivative. Okay, so let's use this secant method. Okay, so secant method. So again, you can split your solution in or you can use the same technique as we have used it here. So let me delete all these things from here. Okay, and how we can find the xi plus 1? Here we should keep this equation in front of us. This is f of x multiplied by xi minus 1 divided by this. So we can either use this technique, or we can use this technique, whatever you feel, but in this case you have to put all these values, and you should be knowing that what is x. For example, this is x minus 1. This is given in the question. In the question you have this x minus 1 0, the first value, the next value is 1, so it means the first two values are already given to us. We don't need to compute them. For example, this is the minus 1 value, and this is the xi, and this is xi minus 1, so we have to use this value. Okay, this is the third iteration. You can control C, control V. Again, I want to explain you, either you can split your solution this way. If you feel comfortable, you can first find xi. You can put it here, fxi minus 1, then fxi, then xi, then fxi, and then you can find out xi plus 1. Or you can use this way, whatever way you find better. For example, I think it's easier to use this way, and this one needs a little bit complication, so let's use this one, because I think you can apply that one by yourself. Okay, so how we can find out xi plus 1? So in xi plus 1 we actually have this equation. So xi minus fxi multiplied by this, divided by this. Okay, so this is xi, this is xi, this is xi minus 1. So this is xi, this value, minus, I'm writing in xi plus 1, this is xi, and this is xi minus 1. Okay, so next is f of x. So f of x is 2.718 just to the power minus xi minus xi. So this is actually, this whole expression is fxi and multiplied by xi minus xi minus 1. So this should be multiplied, this expression should be multiplied by xi minus xi minus 1. So this is here. Okay, yeah, and then divided by fxi minus fxi minus 1. So again, you can just copy all this expression here. This is actually the fxi divided by fxi. Okay, fxi minus fxi minus 1. So from here, instead of G27, you have to make it G26, because this cell is actually xi minus 1. So if I just put a big bracket, I say enter, so yeah, now you can see this is the next value, xi plus 1, and then you can just compute the next values. You can apply the true error. For example, the true error in this case would be 1, the true value minus this value divided by the true value. Okay, let's apply here and make some more trials. So here we can see that at the 5th iteration the solution has been converged, or here you can find this solution. So this is the way how we can solve the same problem using the secant method, and you can also compare that which method is accurate. For example, the Newton Raphson method is a little bit easier and it converges very fast compared to the secant method, because the secant method we have a very long expression. Okay, the next method is the modified secant method. So in modified secant method we have this expression. This is again the definition of error. We add the definition of derivative, we add one very small increment which is called as delta, and this is a very small fraction that we add into the into our values, and we find out fxi. Okay, so this is the equation. If we use this definition of derivative, and if we put this derivative in the Newton Raphson equation back in this equation here, so and we simplify this, so we will get that modified secant method expression, this value. Okay, so let's use this expression and we find out the solution for the modified secant. Let me put this expression here. Okay, so okay, so next is the modified secant method. Modified secant method, and this method you can apply. For example, let's see, again in this case it's better because we have so many terms, so I would recommend you to use the split up technique, in which we split our solution into various parts and then we combine in the end. For example, just say this is actually iteration. Okay, and then we have xi, and then we need delta xi. Let me insert this symbol if I can find it easily, or you can look more. Yeah, it's here, inserts. Okay, delta xi. Okay, so and then I just want to make it smaller. Okay, so this is delta xi, and then we can find, now we have delta xi, we can find fxi. Okay, and then what we need this function f x I plus okay here, yeah, so f xi plus delta xi. Okay, and then we can find xi plus 1. So this is the first iteration. For the first iteration we have the values. For example, in this question, yeah, for the first iteration the value is 1 and the very small increment is 0.01. so this very small increment is the xi is, I believe it's 1. Yeah, here it's 1, and then the very small increment, it is actually equal to 1 multiplied by 0.01. this is delta. So, or let's make it more simple, 0.01 the delta multiplied by xi. Okay, and now you can find fxi. Again, fxi, you have the same function, 2.718 multiplied by raised to the power minus xi minus xi. So this is actually fxi. Okay, and then we have this value. So but before finding directly this value, we can, or you can use it, or you can add one more cell here. For example, this cell is, say, xi plus delta xi. Okay, so this will be equal to xi plus delta xi. Okay, and then you can find out, you can use this same expression here, but here it should be, this value should be this one, and this value will be xi. Okay, so now we can find out fxi plus 1, and this will be equal to xi minus delta, okay, multiplied by this value divided by this value minus this value. Okay, so this is the next root. Again, for the next iteration, now here the next iteration, now the xi, this value will be this xi plus 1. Okay, because now we are going for the next trial, so just for this case you will make these changes, and then all other things you can just control C and control V. You can also find out the true error and the approximate error. For example, the true error, you can say the true error, for example, the true error should be true value minus, okay, it's fine, it's already here. And the approximate error, you can also find the approximate error. For example, you can also find for this case the approximate error. How? You can find this is the current value, this value minus this is the previous value is here divided by the current value, this one. Okay, and then you can apply. So if you make one more trial, so let's see what happens. Okay, so now our true error is almost 0 and the approximate error is 0.02%. so this is how we can use the modified secant method in order to find out the roots of this equation. Okay, so this concludes all this tutorial, and I hope you can use this method, all these methods, in order to find out the roots of the equation. Thank you.